EPSP Connects group. We as a group aim to provide regular virtual events for the global surface process research community that bring us together to share research experiences and advice. Joining me as co-hosts for this event is Dr. Roberto Fernandez, who is running the Zoom, and Dr. Michelle Melendez Bernardo, who will help field questions from you during and after today's presentations. Michelle, do you want to go ahead and introduce yourself briefly?
Yeah, sure. Thank you, Tyler. Oh, well, I'm not a doctor yet. I'm a PhD candidate at the University of Illinois Urbana-Champaign in the program of geography. So hopefully I will defend soon. But yes, please, if you have questions throughout the presentation, please go ahead and type them into the chat. We will read them out after the presentations. And if you prefer, you can also mute yourself and ask a question. We also have this live streaming on YouTube where you can type questions in there.
Okay, yeah, so please, as you come up with questions, go ahead and enter them into the chat and we will get to them later. So today we are excited. We have two science talks that highlight the unique capability of synthetic aperture radar and its derivative technique, if I can say that, called interferometric SAR or INSAR, both of which are imaging systems that provide high temporal frequency and can detect relatively small changes to the land surface. We thought this is a timely topic as we were awaiting the launch of the new SAR satellite, NISAR, which will provide yet higher spatial resolution. And there continue to be new satellites launched all the time. We are also, sorry, excuse me. So yes, we are excited to hear from two speakers today. We will start with Dr. Matthew Morris, who is a project geologist with the Utah Geological Survey. And then at roughly 1/2 we will hear from Dr. Joan Marie Del Vecchio, who is an assistant professor at the College of William and Mary. Each speaker will talk for about 20 minutes, followed by a brief Q&A. We will first hear from Matthew, and then Joan Marie will start at 1/2. I will now turn it over to Matthew.
All right. Can you hear me, Tyler?
Yes, we can hear you and we can see your screen.
Awesome. Hey, thanks everybody. And just in a sad note, NISAR was supposed to be launched on my birthday and then they delayed the launch. So, oh well. No surprises there if you've been following the NISAR drama. Well, thanks everybody for coming, and thank you again to the conveners for providing me this opportunity to give a talk on the subject. I'll be talking today about a specific recent study I was involved in about a landslide in Rocky Mountain National Park in Colorado here in the United States that took place on, as you can see, June 28th. And I really want to call out a lot of my co-authors who are listed below. And particularly for the INSAR portion of the talk, I'll be leaning a lot on work developed by Quinn Brencher and Al Handwerger. But I'll also be mentioning the contributions and talking about the contributions of everybody involved. And this work, if you're more interested and curious, this work is covered in our recent Earth Surface Dynamics paper that came out late last year. You can see it was quite a diverse group of folks. I was very excited to work with people with so many backgrounds and experiences. And there's also a second paper published about this landslide that came out of the US Geological Survey. You can see here on the right by Kate Alstad and others. Both papers are very interesting in how they study a landslide from different angles and come to similar conclusions. Just briefly, here's an example of a picture of the landslide that took place on the 28th of June. This is from early July, so it's just a few days later, just to highlight the area that was evacuated by the landslide here. This is Hallett Peak, which is a very common hiking destination. And then the toe of the deposit is located down here. And if you're a big into rock climbing or bouldering, the area below this is a well-known climbing destination. And there were actually climbers on these boulders on the day of the landslide, which is a little too exciting for me. But some of their video was key for the USGS study, actually. Just to provide a little bit of geography, we're going to work through this figure counterclockwise. My master's advisor said, never take a figure out of a paper and put it in a talk. Well, I'm not following advice like that today. But lower 48 United States, state of Colorado is located right here. And if you've ever been to a GSA meeting in Denver, we're going to focus on an area about 80 kilometers away from Denver and Rocky Mountain National Park, the black boundary here. And this is the main area of focus, which is blown up here. This is Chaos Canyon, which is well named for the numerous large boulders and rocky terrain. And actually the slope that failed in a landslide is located here in this dashed line. And I'll go through what the other points mean throughout the talk. But Lake Haiaha will be mentioned several times as a point of reference for observations of the landslide actually taking place. We were really lucky. There's 1 meter LiDAR that was flown before the failure took place. So this is that LiDAR data set from, I think, 2019. And the landslide is basically this landform. So within the black line is the area that failed catastrophically in 2022. And the sort of name Chaos Canyon comes from these large boulders that might be remnants of other landslides potentially. And again, Lake Haiaha, popular hiking destination, and there were some eyewitnesses to this landslide who took video looking across the valley. Background geology for this area is some of the oldest rocks in North America, at least in the United States, with this silver plume granite, and the XS here is a biotite schist. The landslide took place across the boundary between these two rock types. It was mapped previously by a geologic mapper as Quaternary talus, as opposed to this deposit down here, which was mapped as a rock glacier. But we'll make an argument for the presence of permafrost and the active processes of the landslide. And there's also what engineering geologists would call an adverse dip, where the foliation in the schist is dipping towards the canyon. So that's potentially at play as well in the actual basal slip surface, which I'll show some pictures of later on in the talk. What really motivated the study was, I feel like a lot of science these days, is a video on Twitter, or the social network formerly known as Twitter. This is from Lake Haiaha. The person will zoom in several times, but you can see this big deposit moving slowly down the slope. There's very large boulders in here. And you know, this is just like the nice thing about being in the age we are, where science is often captured by citizens out in the wild, and then that gives earth scientists something to start a study with. So if we go back and watch that one more time, you'll notice the landslide's translating relatively slowly. It's not, doesn't appear very fluid in form. It's sort of just sliding down the slope. This, if you've ever met a gentleman named Harrison Gray, is all his fault, I will say. He sent me this video on Twitter, and I proceeded to connect with other scientists on Twitter, and that became sort of the circling group of co-authors, and then a few other people joined through different connections. But I really thought this was a fun, exciting study to really get started via social network. And it's too bad what's happened to Twitter more recently. But we got a paper out of this, which is pretty fun. A bit more of imagery before and after. So this is a Google Earth perspective view. Again, a reminder, this is the landform that's going to fail catastrophically. And you'll see it has a very steep front. Some inventories of rock glaciers mapped this as a rock glacier. For various reasons, we decided not to classify it as a rock glacier, and maybe it's a piece of an older landslide that may explain some of these larger blocks. And if we shift to the post-failure image, here we go. So let's go back and forth, back, and then post-failure. So you can see this large, very steep landform has moved down the slope. There's a little pond here that suddenly turns aquamarine blue due to rock flower. The same thing happened to Lake Haiaha. And what was really cool about this landslide is how quickly people were able to get out and respond. So within a week, Benjamin Kampfertz and Ben Lehman, who were postdocs at CU Boulder at the time, were out in the field taking photos for photogrammetry. And they were part of this group that we connected through Twitter with. And then I was able to go out basically the same day and take another slew of photos. And Ben and Benjamin very quickly put together a brief geomorphic map of the landslide's character in terms of where was the deposit, where were the stable rocks from previous landslides, what was going on in the failure zone. For instance, there's a lot of snow, but also a lot of running water over what looked like a dipping or foliation plane in the bedrock. And this really brought on a series of questions that as a group, we came together in a bunch of Zoom meetings to discuss. And this sort of started as a general landslide inquiry. And we asked, what are some fundamental questions about this landslide? For instance, was it moving prior to collapse, or did it collapse catastrophically just out of the blue? Were there any climatic trends that led into this collapse? And then can we constrain the volume of the slide, and what can we say about the volume of the slide? And then what do we say about the presence or absence of permafrost? So again, this landform had been mapped as a rock glacier previously. Is it a rock glacier, or is it some other periglacial landform, or is it just a remnant of an older landslide? And then what can we say about the actual initiation of the landslide through some modeling work? And then finally, what does all of this tell us about the future of alpine stability in a warming climate? And I want to just call out each of the co-authors for the parts that they contributed to. And specifically, most of my talk will be on this question of, was the landslide moving prior to collapse? And how can we use INSAR and other remote sensing methods to get at the answer? So very quickly, after assembling this great team of scientists, we were able to pull Planet Earth, Planet Labs imagery of a series of years previous to failure. So just again, the arrow pointing to the landform of interest. And so I'll only walk through this once, but keep your eyes peeled on the slope. And you'll very quickly see there's a lot of translation taking place. And then the failure happens. So very quickly, we were able to answer at least yes, it appears the landform was moving prior to collapse, but how quickly, and is it accelerating into 2022, which is a key question for landslides. Is it accelerating? Is it linear and then fails in terms of velocity? So this actually changed our question. Instead of yes or no, is it moving? How quickly was the landslide moving prior to collapse? And again, we chose two approaches. So we focused in on INSAR initially, and this was led by Quinn and Al. And then in addition to INSAR, we approached pixel tracking with those amazing planet imagery images that we have, and then also some Google Earth imagery. And just a reminder, actually, Tyler already covered this, but here's the INSAR acronym spelled out. And we're mostly going to rely on the Sentinel A and B satellites for this discussion. Just a brief primer for the audience in terms of what INSAR is and how it works. So this is a bit of an older image from Gareth Fooning at UC Riverside, but generally INSAR is a radar product, and you have a satellite that circles the globe on periodic, certain periods, and it eventually covers the entire globe. And constantly it's bouncing a radar signal back to the surface and back, and measuring what is the phase of that signal, or what is the time it's expecting the signal to come back. And any mistakes in the description of INSAR are because I'm not an INSAR specialist, so please forgive me if I screw this up. But if you're sending a signal down to the Earth and then you circle the Earth and 12 days later you come back and you bounce a signal off the surface and the phase has shifted, that's an indicator of some surface deformation. So in this case, in this example, if you have a fault that ruptures the surface, or in the case of our landslide, has the landslide moved away or towards the satellite? And in phase space, you end up combining the two images from the first pass and the second pass, and that gives you what's called a wrapped interferogram, which is probably familiar to some of you, this sort of image of fringing colors, which you could almost consider like a topo map in the sense of as you go across multiple colors, you're accumulating change potentially. But what we want to do with a wrapped interferogram is actually unwrap it and get at an image of true horizontal vertical deformation. So that's a bit more of a computational step that I'll talk about in a moment, but this is your first product looking at INSAR data. And additionally, you have to think about where is the satellite relative to the landform you're imaging. So as satellite goes around the Earth and it first comes over the horizon in what's called an ascending orbit. So if the satellite is coming over the horizon and looking down at the landslide, that's the ascending orbit. And then as it continues across the sky and goes towards the next horizon as it descends, that's a descending orbit. And so you get two measurements of the line of sight, basically. And so initial velocity will be a line of sight velocity towards or away from the satellite. And the other consideration is whether the landform could actually be shaded entirely from your line of sight. So you could imagine some very deep clefts or basically cirque head walls could shade an entire landform from a satellite if the geometry was not just so, or not over the geometry was really unfortunate. Luckily, we had really good coverage of this landslide, so we were able to image it from both ascending and descending tracks, which I'll discuss here in a second. And the first thing that Quinn did is he looked at an ascending track signal. And so this is actually the wrapped interferogram across 12 days. So this is all in phase space. We're not talking velocities at this point. And he was able to say that this basically phase deformation that we see here, or phase offset, could be 10 centimeters of movement in 12 days. And so that's a very fast movement rate. And this is only a 12-day period in 2018. And if we move forward to velocity space, so this is now an unwrapped interferogram, and red and blue mean red meaning motion away from a satellite, blue motion towards a satellite. So this is line of sight. And within the actual landslide deposit, Quinn was able to isolate some velocities, but there's actually a lot of scatter once you do the unwrapping process. So there's a sort of a blue and red static in here as compared with this rock glacier, which we know is moving downslope and has a very nice red warm hue to it. And you can measure this based off, okay, what's the standard deviation of velocity within the landslide? And you can notice here, the landslide is this darker green color, indicating it has a really high variability of measured velocity. And the rock glacier actually has really low standard deviation. And then finally, you can look at the coherence of your signal. So how well are your interferograms comparing to each other? And unfortunately, our landslide had really low coherence. So it's this really bright white color, indicating that our results may not be very robust, unfortunately. And one hypothesis for this is actually the landslide may be moving too quickly. So we have 10 centimeters in 12 days, and it could be, if we compare multiple years, it's moving too quickly for us to actually measure velocities on accurately. And Al and Quinn expanded on this. They looked at a bunch of different tracks. So 2 ascending and 1 descending track, again, showing a lot of variability in terms of a lot of high standard deviation and really low coherence across every possible track. And again, this could mean velocities are just too high for us to measure with INSAR. And this is all related to what's the wavelength of your radar signal. And if we look at a few more wrapped interferograms, so here you can see sort of a high variability in the colors of the phase. It's not a nice, nice consistent signal, meaning that we're really losing resolution. Basically, the material is moving too quickly away from the satellite, and we can't resolve velocities accurately. This was really an unfortunate experience because we had really hoped that INSAR could provide some rates for us, but we ended up not using it in the end to provide basically rates of deformation prior to collapse. And this is an important consideration if you're looking to pursue INSAR in your own studies, is that so the satellites we're using have a wavelength of about 5.6 centimeters, and you can't detect deformation of a rate of a deformation that's more than half of that wavelength, so greater than 2.8 centimeters. And if you do some math, if it's moving more than 2.8 centimeters in 12 days, you're not going to accurately resolve rates of deformation, which was all news to me being an INSAR novice in this study, but it was really important learning experience. And because of this, we ended up opting for a different method. So we have first really good Google Earth imagery across the landslide for several years. And so Jeff Moore actually extracted Google Earth images from 2016 to 2019 and was able to find a really good image correlation. And basically these 3 figures here are some of the results. So the first figure is, again, here's the landform that fails. And here's a heat map of horizontal deformation across 3 years. So parts of our landslide are actually moving at 10 meters in 3 years. So it's not a surprise that we saw real struggles with INSAR. And here's a nice vector plot trying to track movement across pixels, showing that there's not only the top of the landform is moving, but the base of that steep slope is moving, indicating both internal deformation and potentially basal sliding are at play. And I know I'm moving quickly through these results, but this was Al's contribution in pixel tracking, is basically looking at bulk velocities across time using planet imagery. Back to almost 2017, there's indications of actual movement of the landform of interest. And after 2019, we see an acceleration in movement all the way up to 17 meters per year. So if you're familiar with like 1/over velocity measurements for when will landslides fail, we're basically ramping up in acceleration. So it's not a total surprise that by 2022, we see a failure in the landform. And I should say this really matches well with the USGS study. They were able to go back farther in time. So this is from Alstad 2023. And they really point out that this landform started moving in the late 90s, almost the turn of the century. and our rates match pretty well. They have a little bit more data from 2022. So this is all to say, this landform was moving, and it was really moving quickly at 17 meters a year in 2021. And it started moving maybe even back in 1998. But I also want to say, what other things did we do in addition to NSAR that helped us understand the processes of this landform and the landslide? And with this, I'm going to talk a little bit about climatic trends. We're really lucky this landslide had climate stations very close by, which let us actually conduct a bit more in-depth analysis of what was taking place in Chaos Canyon. And in this figure, I just highlighted in blue, this is 2022, with the last 20 years of the climate record behind it. And 2022 wasn't particularly warm, and there wasn't anything in temperature space that really highlights why the landslide failed that year. But if we look at snowmelt ablation rates, if you look at, again, blue is 2022, we're ramping up to peak snowmelt in late June. And 2022, again, was like an average year in terms of snowmelt. There wasn't a massive amount, and there wasn't a very low amount. But this really got us thinking that maybe groundwater had some part to play in the story. And again, satellite imagery really just bulking up the idea that snowmelt is at its maximum pace, basically, or very close to it as we get to late June and when the landslide failed. Leif Anderson at the University of Utah did some modeling work. He was able to build a 3D model of the slide in, I think it's called Slide 3D software, and show that without any major groundwater, there's still a factor of safety greater than 1, and the landslide slope does not fail. But if you introduce even the smallest amount of groundwater, you reach a factor of safety less than 1, and the slope fails. So again, supporting this hypothesis of the importance of groundwater. And we also want to know how much we're changing alpine landscapes with a landslide like this. So we leaned on Ben and Benjamin's photogrammetry experience. They were able to get out within a week of the landslide and collect sites, photos from a bunch of different sites looking directly across at the landslide, and really some amazing fieldwork opportunities, to be honest, and constructed a really nice DEM of difference, highlighting here's an area here where erosion took place, and the area in which the landslide spread out and deposited, and finding some really large numbers on movement. So roughly about 1.3 million cubic meters of erosion took place, and about 1.2 million cubic meters of deposition. So the landslide really spread out, and there is some error in our measurements, but we're moving a fair amount of the hillside down into the valley. So potentially this speaks to like how rapidly we could see landscape evolution and alpine systems change if this is all part of climate warming, for instance. And these numbers work really well with the USGS study as well. For those familiar with some of the some plots like this in terms of landslide mobility, the diamond or the small triangle here is our landslide for point of reference in terms of its volume relative to a large data set and its mobility. So it's pretty low on the mobility spectrum. So for reference, this is the Oso landslide from 2014, which many folks are familiar with. Our landslide is not very mobile. Remember, it just slowly translated down the slope. And that means that there's some role for water, perhaps, but not a lot of water in the system, maybe just enough to kick off the slide. And I did want to talk a little bit about, is there actually ice in this landform? And so Irina Overeem did some permafrost modeling to show that there is the potential for permafrost at this altitude. With below 2 meters below the surface, you could have an average temperature below 0, indicating the presence of permafrost. And using that climate sense of like, we're in a warming climate, maybe permafrost is thawing. Permafrost thaw would allow for greater contribution of snowmelt into this landform, and then actually all the way maybe to the base if you just have sporadic patches of permafrost versus an entire lens of permafrost across the landform. And luckily, there are actually some really nice field observations to support this. This is from Alstad 2023. So this is a video from a rock climber who was standing below the landslide when it took place. And they noticed these large boulders, which just look like rocks on June 28th. But if you come back in mid-July, when the USGS did their survey, those rocks are now piles of debris. These are called mallards, I believe, basically big chunks of permafrost that thawed and melted and left all their interstitial sediment as these little cones, which is kind of a cool observation. And it supports our modeling work that permafrost was at play, or at least present in this landform, and maybe contributed to some extent to failure. And then I want to end with sort of, what does this story tell us about the future of alpine landforms and their stability in a warming climate? Well, at the site of the landslide, the average temperature has increased over the last 30 years of record. So you can see that, in the early 2000s, maybe 2005, you switch over to an average temperature greater than 0 Celsius. And this is backed up by, I calculated what is the temperature anomaly. And so about 2005, you get to positive temperature anomalies over the last 30 years for the average annual temperature. And then another measure here, this is positive degree day sums, which is a helpful measure for snowmelt. We're having increasing positive degree day sum anomalies where we're having more rapid snowmelt than in the past. Again, all of this could contribute to more groundwater, more water availability to change the stability of alpine landforms. And again, what's really interesting is we've had a large discussion as a community about landslides and rockfalls in the Alps, in Alaska, and maybe some in the Andes as well, related to climate change. And there's good documentation of increased rockfall. But in the lower 48, we haven't seen a similar increase, or at least not that I've seen documented. And so I want to really say that hopefully this is an opportunity for us to focus in on our alpine landscapes, increase our monitoring of landform change, rockfall, and landslides, and potentially these systems could be activating in surprising and unexpected ways. And with that, I know I'm running a little bit late here, maybe, but I want to say there's some time for questions, and happy to take any questions.
Yes, thank you, Matthew. That was a really great synthesis of SAR data, satellite imagery, and some field observations. If you do have questions, go ahead and put them in the chat. We have, a couple of minutes until we're going to get going on the next talk. But I guess I'll go with a question, Matthew. You mentioned that the INSAR was a little bit too fine of a resolution to detect the change. But you were lucky to have access to planet imagery that was able to fill that gap.
Correct.
Would in the absence of having that, would you have been able to put a lower bound on the velocity just using INSAR?
I believe so. I think we could say it was faster than a certain rate, and we could also try to break up the time series into just a discrete. So the satellite return interval is 12 days for Colorado. So we could say it moves this much over 12-day periods in the summer, but wouldn't give us like as much of a time integrated signal as we had hoped for. That is possible, I believe. As the non-INSAR expert. And if you have other questions about INSAR, feel free to reach out to me, but I'll probably forward you to like Quinn, who's very experienced, or Al.
Yeah, well, let me just say, this was the intention of this event is to highlight the utility of INSAR for surface processes, and I think you did a great job of explaining how it works.
Thanks, Tyler.
So you're not expected to be an INSAR expert here.
Okay, I feel in a safe space. I think there's a question in the chat, actually.
Actually, there is another question. Thank you, Matthew. It's about the methodology of your permafrost modeling.
Yeah, so I think this is from Michael Powers, and Michael, I should know. I don't recall which code Arena used, but I can reference the paper after this if you want. I can try to send you a chat and send you the code which code she used. I know it's a published permafrost modeling code, but I think she just did a 2D model. We talked about doing a 3D model, but didn't get there with this work. Oh yeah, that's correct. Joan Marie, thank you so much.
It might be good if you have papers that you're referencing in the talk, feel free to, put the links on the chat so people can access them right away.
Yeah, will do.
Yeah, so there's one. Let's go ahead and take this one more question from Kyra Bornon. Thanks for the cool talk, Matthew. Were y'all able to use the INSAR to look at other moving features nearby, like if there were other landslide features that started moving around the same time?
Okay, yeah, great question, Kyra. So we did see that rock glacier moving to the north. We didn't do a full inventory of Rocky Mountain National Park. That was something we sort of left into the discussion, as this is a great opportunity to sort of expand INSAR scope across our alpine systems. But we didn't we didn't expand that scope. I should have started also with this work was entirely unfunded and volunteer time. So Quinn was doing this on the side of his PhD, and we were appreciative of any time he could commit. But I think there are opportunities for continued monitoring and expanding our monitoring of alpine landscapes to look for other landforms that are unstable. And Al and Quinn are both now experts in using INSAR on rock glaciers and rock glacier deformation. So that's another type of landform to continue to monitor in these systems. And with that, I think I'm out of time. So thank you so much, everybody.
Yes, thank you again, Matthew. And we will go ahead and turn it over to Joan Marie Del Vecchio.
All right, I'm sharing. I've got my screen. Can you see it?
You're sharing, we can hear you, and we
hide
can see
floating.
your screen.
Awesome.
good.
Okay, great. Well, thank you so much, Matthew, for the introduction to INSAR. So I can kind of like go over that kind of quickly. And thank you so much for the organizers. I also think that this is a cool, timely topic. I'm a big fan of using just satellites in general to study landscapes that sometimes we can't get to. And SAR and INSAR are definitely one of the many tools that we could use to study landscapes. And I'm somebody who thinks about change in permafrost landscapes. So alpine, Arctic landscapes, cold places that are changing with changing climate. But much like some of these alpine peaks, it's usually, remote characterization is the rule rather than the exception. So cool to study with satellites. I'm going to be presenting some work that I did sort of led by the intrepid Joel Rowland at Los Alamos, and all of the INSAR work is done by Simon Zwiebeck at Alaska, and you'll see the other folks listed on the papers that have contributed to this work. Really happy to share the work that my co-authors and I have done on this topic. And I'm going to try to progress. Okay, so in addition to SAR and INSAR, we've got other ways that we can watch the Arctic change. And so I also was going to show a planet time lapse, but maybe I've got my video's not playing now because I've got this like laser pointer. Maybe I won't do that. Let's watch this. All right, so we've got these small satellites orbiting the planet almost daily, taking pictures of the Arctic in a way that we've never had data before. We also have these photogrammetric digital elevation models that folks at the Polar Geospatial Center have put together of the Arctic and the Antarctic. We've got more data than ever before to study the changing permafrost landscapes of our planet. And today I'm going to be telling you a little bit about how we use INSAR to do this and how I've used INSAR to study permafrost landscapes. So great introduction before. If you missed it, right, you've got a satellite that, zaps the ground, comes back 12 days later, zaps the ground again. If something has moved, there's been a phase shift in that wave. You get these like little rings of the phase shift. And if you can say something about the underlying topography, you can actually turn those rings into absolute deformation. And so the ingredients for a deformation map derived from INSAR is a before and after satellite pass, and that happens about every 12 days. A digital elevation model to remove the phase associated with the topography so that you can kind of make this nice map over here like the USGS has that is just sort of the change in topography. And then the most important ingredient for your deformation map is definitely someone to help you make that if you're a geomorphologist, because it turns out the codes are out there. So you can kind of figure these things out on your own, but you really want to find a collaborator to help you out. And my collaborator here is Simon Zwiebeck. And so, like I said, he's the one who's done making all of these wonderful maps and data. I'm just the geomorphologist interpreting them. So permafrost is kind of neat, and people have always sort of appreciated that as the seasons come and go up in the Arctic, permafrost landscapes sort of seasonally inhale and exhale with freeze and thaw on the order of 1s or even 10s of centimeters, because guess what? There's tons of frozen water under the ground, and when that frozen water thaws, you get subsidence, and then during the fall, it comes back up. And so this is a paper by some folks who have used INSAR just to say, hey, guess what? As the surface comes and goes seasonally, we can actually estimate how much water permafrost is storing. And so this is sort of our null hypothesis that we're going to have inflation and deflation of permafrost landscapes seasonally as the phase of water goes from solid to liquid. However, there is the potential to track permanent displacement, say if something is thawing and that ice isn't coming back year after year, or you've had some sort of erosion event. And so when we ask about how to use INSAR in permafrost landscapes to track how the landscape is changing, we have to remember these two things, that there's a seasonal signal that you have to separate from any sort of like long-term disturbance or deformation that you might track year over year. And so I have done some field work in the Seward Peninsula in Western Alaska, and this is sort of Joel Rowland's like site. He's got this watershed down the Teller Road, you know, going from Nome, Alaska, and this place is like totally falling apart. These are some images that I took from some field work in 2019. It's in discontinuous permafrost. It's fairly warm permafrost, and it is warming, you know, at maybe half a degree or a tenth of a degree or a fifth of a degree a year. We've had a couple of warm and very wet seasons, and in particular, when I visited in 2019, it was particularly wet. We visited just after a huge rainstorm that happened at the beginning of the month, and we saw all of this disturbance on the landscape. Some of the pictures that you're seeing on the screen here. And so, you know, we went out all across this landscape. We made our field observations, and we came back to sort of like process what we'd seen. We wanted to know, what are some of the climate or topographic drivers of some of these big disturbances in this landscape? You know, can we attribute some of these slope failures and new gullying and incision to warming, or is it just, you know, slopes doing slopes, and maybe it has nothing to do with, you know, maybe it has to do with rain more than temperature, or maybe these are just, you know, threshold landscape positions that are going to erode no matter what. So those were some of the questions that we were trying to tackle with this work. So kind of like Matthew, I'm going to plug some of the non-INSAR fun that we've done for this work. And so we've got one paper on this in Earth Surface Dynamics, where in addition to some of the satellite work, we made some painstaking field measurements. We took GPS of ground control points that moved year over year, telling us that some of the surface displacements in this landscape are on the order of 10 or 20 centimeters a year, which like seems really crazy and unbelievable. We kind of could see solifluction lobes blebbing out over the years. And that was some work that we did as a group. And then later, there was a group from Lawrence Berkeley National Lab that set out these like really neat sort of probes into the permafrost all across the landscape to actually see if there was displacement and like stress on these probes. And they found something similar where we actually had some surface displacements that were pushing 10, 20 centimeters in a year. And so if you want to learn about how permafrost landscapes work, I suggest checking out these two papers. You can kind of start to wrap your head around what happens when a landscape like is totally falling apart in front of our eyes. But in terms of INSAR, one of the things also that Matthew sort of highlighted here is that INSAR displacements, if you're trying to calculate them, are going to be biased by the satellite line of sight. And so the watershed that we were working in was facing east. And that is like no bueno when it comes to using a satellite whose line of sight might be due west. And this is, you know, I'm also trying to explain the sort of complicated like constructive versus destructive interference that comes from if you're looking directly at a surface versus a surface that's away. I looked at this figure and I really just saw like this, and it was like hard to wrap my mind around what was going on. But the sort of the take home message is that, you know, depending on the aspect of that surface, you are going to either underestimate or potentially overestimate the displacement. So we had to sort of abandon our east-facing watershed, not really conducive to doing some time series analysis with INSAR, but instead we used 5 nearby sites on a similar hill slope, but a more favorable aspect so that we can do some time series analysis. And so this is the time series that Simon gave for us. So each of these is 2017, 2018, and 2019 over sort of the warm season. So starting in June, ending in September. And you've got the the peak rainstorm here in 2019. And so this green line is like potentially maybe responding to this big rainstorm that we had. And so we kind of saw this first and we were like, oh, wow. So maybe like rainfall is driving, you know, some displacement in this landscape. Be like, what are the other sort of climate records we have that we can cross-reference with these displacements that we're seeing across this landscape? But it turns out that like when, you know, I tried, you know, I scratched my head over this. I have sort of cumulative precipitation. I have mean temperature, you know, all sorts of ways to try to describe how it rained or how warm it was prior to these satellite passes to get the displacement rates. And my takeaway is that there's no real smoking gun for a climate driver in this displacement time series. You know, the only thing that like I sort of could think about is that, you know, cumulative displacement kind of mirrors cumulative precipitation, you know, potentially that's telling us that there is some moisture or precipitation event that might drive, you know, overall displacements over the course of a season. But, you know, when we looked at when there were heat waves or times when it was like really warm, like sustained warm or a spike in warm, you know, sometimes that seemed to be associated with displacement and sometimes it didn't. So it was a pretty confusing data set to interpret. And quite frankly, I kind of left it saying, I don't really think I saw much of a signal. And in fact, you know, you're all welcome to read the multivariate tea leaves. If you got the, you know, time series analysis skills, if you've got the statistical skills, you're more than welcome to check out. The data is on the GitHub repo, and maybe there's something more to be discovered in this time series. But we kind of walked away saying like, you know, there was no smoking gun in terms of either temperature or rainfall for this. So that was a time series, and that was looking like over the course of a season. But I also wanted to know, like, is there something driving some of these permanent displacements, like those landslides we were seeing, those erosion events? Like, what is driving why we might see those erosion events? And so this was a second paper that we came out with last year in JGR, and we're kind of focusing on this like alternative hypothesis that like, if we want to see permanent displacement, we should look at the same time year over year. So instead of seeing any sort of seasonal signal, we're going to see any permanent displacement. So we compared pixel-wise position of the ground during late July, hopefully thinking that all of our subsidence may have happened by that time, so that our signal would purely be permanent erosion. I made a little geomorphic map of the area, and Simon was very clever. And where I mapped bedrock Torres outcropping, he sort of used those as reference points for zero displacement. And so we've kind of got a little bit of ground truthing as well for some of the displacements you're going to see on this map that he made, this beautiful map of displacement that you can see here. So this is the INSAR displacement over a pretty big portion of our study area, draped over a satellite image, and you can see that, you know, there are bright spots, there are dark spots, and sort of at the macro scale, 100%, you are seeing some line of sight bias. And so a lot of the big displacements are on some of the east-facing slopes, the small displacements are on some of the west-facing slopes. So if I was going to try to disentangle this from any sort of geomorphology, I was going to have to get a little clever with how I worked with this. So I used LC topo tools to delineate watershed basins and channels. And what I noticed was that, you know, there are portions of the landscape that seem to be responding to maybe some sort of like passing nick point. Some base level change signal is going through this landscape. We've got some convexities in the stream profiles. We've got steeper slopes in some places, you know. Maybe there's a short-term INSAR displacement signature that might connect to some of these steeper or less steep hill slopes. So in order to counteract the line of sight bias, I grouped all of the basins into which way they were facing. And when I did that, I then calculated a like displacement z-score. So what that means is that I said, okay, for all the north-facing basins, like I basically calculated how many standard deviations they were for the mean of that aspect. And so in that way, I'd like to think that I sort of counteracted the line of sight bias by getting everyone to, you know, a similar 0, and then saying which basins, you know, considering their aspect, did they move more or less compared to other basins of that aspect. And it turns out that when I plotted up that data, there didn't really seem to be an apparent base level or slope control on movement at that scale. So, you know, we didn't really see that there was sort of this like something that you might expect to be a long-term geomorphic driver of change wasn't really panning out in any short-term data. So I said, all right. So I scratched my head for a little bit and I said, all right, what if I take this map and I group all of the pixels in this map by their sort of like geomorphic zone, geomorphic domain. And I started to see some things here. So I've got my laser pointer here. So I manually mapped some channel heads on this just so that you can see we've got drainage area on the x-axis. And so we're getting, you know, more and more wetness, more and more upslope contributing area on the x-axis. And then you've just got topographic slope on the y-axis. And so this like big black hole right here is actually some of those bedrock tors. They're a little bit steep and they're not moving. But we do have this hotspot right here. Something is happening that is in the space, sort of not quite hill slopes, but also not quite channels, right? These are upslope, you know, system of channel heads. And consistently, these points on the landscape are being displaced quite a bit. And when I sort of zoomed into this landscape, I found that these displacement hotspots are in this sort of transition space between hill slopes and channels. And in a permafrost landscape, this zone is actually fairly unique in that it's like big, broad, and marked by these eco-hydrogeomorphic features known as water tracks. And here I have to put on my sort of like tinfoil hat, my red string to tell you all about water tracks. Okay, so water tracks are these like permafrost features. They transport water without carving valleys and creating convergent topography. They sort of come out as these like very like finely spaced flow paths. And in permafrost landscapes, early season snowmelt isn't really incising frozen hill slopes. The tundra vegetation is nice and porous. And what that means is that water's moving through the system, but not doing a lot of incision. And so you can see we've got a bunch of these flow paths, these sort of like hairy things coming off of the hill slope. But when you look at the actual topography, it's quite smooth. It hasn't been incised because the ground is frozen. The water can't incise when the ground is frozen. And so these things have been described in the North Slope of Alaska. They've been described in Antarctica. Maybe they have planetary analogs on Mars in recurring slope lineae. But, you know, all of this is to say is that water tracks are these like really interesting, unique flow paths in permafrost landscapes that are between hill slopes and channels. You know, they're between one and the other. And in my landscape and in the landscapes of others who are working on permafrost landscapes that have water tracks, it seems like there's a lot of erosional disturbance within water tracks. So, you know, we have like trends in warming, trends in wetting, and these are two forces that are working to sort of disrupt this thing that is like not quite a hill slope, not quite a channel. And we sort of like used this work, this disturbance that is being concentrated in this like geomorphic area to say that, you know, the fact that we have disturbance in water tracks seems to match this sort of prediction that we've made in a recent paper looking all across the Arctic, looking at drainage density all across the Arctic, saying that as you thaw permafrost, as you lower the permafrost table, your landscapes are at risk for increased channelization with permafrost thaw. And the INSAR data really seems to be implying that this is the case. And folks have used satellite and other field data to also say that water tracks seem to be this locus of disturbance. Before I get too much into the final steps, I do want to like throw this little like nugget out here for the geomorphologists. Something that in this paper we talked about that wasn't water track related is that when I grouped everything by slope and saw how slope was modulating disturbance, there's actually like an intermediate slope that has some of the highest displacements. And steep slopes in particular that had little upslope drainage area were relatively stable. And that was surprising to me, but I also think it goes with sort of this idea I've been thinking about in permafrost landscapes that you have a trade-off between steepness and wetness. which is that, if you're really steep, you're probably really well drained. And saturation is actually a really good tool to do movement and displacement in a landscape where if you can raise the pore pressure and do some of this like gelifluction, solifluction, goopy processes that we might be tracking with INSAR, that's sort of you've got the sort of Goldilocks zone where you're both a little bit steep and a little bit wet, and you're maximizing the measurements of displacement that we saw. So that's my story. The sort of looking in the future. So you might be following some of the satellite products that might be coming available. So NASA and JPL are going to put out this new Opera product that will have like an end user displacement product. This will cover the continental US as well as Alaska and within 200 kilometers of that Alaskan border. So potentially we'll all be able to use some of this displacement data to track permafrost landscapes. There are other ways of tracking topographic change in the Arctic. So Arctic DEM has overlapping tiles that you can do DEMs of difference. NASA's got ICESat-2, which is mainly used for mapping ice sheets, but it has a lot of crossovers up in like the high Canadian Arctic. So you might be able to do topographic change detection up there. And there's actually an increasing number of LiDAR flights that are being flown by either the USGS, NOAA, or LTERs up in the Arctic. And so that might be another place that we can like use some of that data. And I'll end here on a plug. I have a grant that is trying to increase or really decrease the learning curve associated with doing scalable and reproducible geomorphology. I'm working with some undergrads who are collecting data up in the Arctic, and we're sort of like writing codes together and making some of the coding and data analysis more accessible. And so I'm hoping that, this is a thing where we can all embrace the more computationally challenging methods that we're going to need in order to check out the Arctic and study how permafrost landscapes are changing. So thanks very much. And I'd be very happy to take any questions.
Great. Thank you, Joan Marie. That was really great. Thank you for taking us on that journey through radar and up to the Arctic with you. That was really, really incredible work that you're doing. We have one quick question from Jakob Putkonen. Nice talk. What is the INSAR footprint or pixel size?
Great question. So it's about 30 meters. So the INSAR footprint is a little big compared to maybe some of the fine scale geomorphic features we're interested. Nonetheless, if you've got some portion of that pixel that's moved a lot, your signal is going to be muted, but you are still going to pick up on that displacement. And so that's sort of what we're hanging our hat on right now.
Okay, and just as a reminder, if you do have questions, please go ahead and put them into the chat as they come to you. So you had mentioned that there's an aspect bias in the satellite data, in the radar data. Did you mention if you're using ascending or descending satellites? And if you use both of them, does that allow you to, does that at least remove them for east versus west?
Good question for Simon.
Apologies for putting
the only thing I can I made that bar chart or the box plot. So whatever Simon may or may not have done to compensate for biases, we still, we had some residual bias.
Yeah. Okay.
So, yeah.
Okay.
Sorry, I can't answer that any further.
Sure. No problem.
Yeah, there is one question from Aidan Scheller. He's asking if you have any insights regarding the uncertainty in INSAR data that might have been caused by dense tundra vegetation.
Ooh, another great question. So I am very much aware that both moisture and vegetation are not great for the signal coherence. I think that Matthew also sort of alluded to, there are certain conditions that make the signal tricky. So for that work, we actually didn't use some years or patches of data that had a lot of scatter and low coherence. Once again, sort of the footprint tells you that, maybe for a stream that's only a couple of meters wide, hopefully you're sort of averaging over that entire signal. But I don't know how to quantify that uncertainty, but I am almost certain that moisture and vegetation do lead to some noisiness in the signal, which makes things challenging.
Thank you.
I guess, Roberto, go ahead if you had a.
No, I just wanted to remind you, there was a question before also related to Matthew's talk about pixel tracking.
Yes, I believe Matthew answered that in the chat, but Matthew, if you want to, I guess we can go ahead and open this up to general questions with regard to both talks, if you'd like now. But Matthew, if you want to address that question.
Yeah, I think I responded in the chat with the proper citations.
Okay, yeah, so if you are interested in that question, go ahead and scroll up through the chat.
Yeah, it was specific to like what method we used for pixel tracking, and we used two different methods, one in Google Earth imagery, and then Al used a more INSAR-based toolkit for doing pixel tracking in the planet imagery.
Okay. Okay. John Marie, I guess I have a question that sort of piggybacks on that last one. Without being an expert in Arctic geomorphology or vegetation, you identified this signal that seems to suggest that that transition between hill slopes and channels has the most motion, correct?
Right.
Is vegetation also tied to that location?
That's good, and probably playing maybe some role. I mean, the map that sort of like heat map that I showed you, it was a fairly like strong signal in that one thing. So like, yes, you will sometimes have shrubs growing where you have either disturbance or where you have overland flow. Sort of the way that this landscape works is that you've got sort of tussock tundra, sedges, grasses, where you don't have like streams, and then like shrubs love the water of streams, and so they show up there. So there is the potential for some like systematic issue, but at the same time, some of those hotspots were not associated with some of these shrubs. And so the fact that the signal is consistent for this like location tells me that it sort of surpasses any like vegetation bias that might be imparted. But it's tough to take like a single pixel and like tell the story of a single pixel. That's why I used like 2 million of them or whatever.
Yes, understood. And those rates of 10 to 20 centimeters a year is such a large signal. That is signal to noise ratio, I imagine, is fairly large for that.
Yeah, I think the INSAR was the INSAR numbers tended to be on the like low ones of centimeters, okay. We were like GPSing 10s and 20 centimeters a year. So what that means is that there are some parts of the landscape that are moving that much, but because of that footprint, you know, there might be like some of it's moving really fast, some of it's moving not so much. So the INSAR sees, I think we actually did this at our watershed, where the INSAR sees, you know, 6 centimeters a year, where we know that there is like a whole gully happening. So INSAR is potentially an underestimate just because of the size of the footprint of a pixel relative to a geomorphic process.
Okay, I think we have time for, let's try to get to 2 more talks. We might go a little over the hour, but there's one from Matthew Morris. Joan Marie, do you see different vegetation or different species in those water tracks, or are they just wetter and that's why they stand out?
Yeah, so depending on where you are in the world, the vegetation contrast like very much tells you where these water tracks are. Sometimes it's just like greener grass versus less green grass. Sometimes it's an entirely like maybe it's shrubby versus not shrubby. In where I work in the Seward Peninsula, it's definitely like a greenness. So like early in the season, these places of enhanced soil moisture get greener. It might not necessarily be a species, but it's like a greenness factor. But I do want to use some of the planet data. You could make like wetness indices. And so I've been like wanting to explore like independent of vegetation. Can you pick out, oh yeah, it's wetter there versus it's just greener, which is what we're using right now.
Yeah, thank you, Jean Mary. We have another question from Bernard Holland. So He said that since snow is a principal source of water, it might be instructive to use insert to document snow thickness and compare it to surface displacement. Do you have or know of experience doing this?
This is maybe a Matthew question. Source of water for, or maybe it's me. I don't know. It could be either.
I'm not sure, Bernard, who you were asking that to, but yeah, I can
sorry.
try and
Sorry. I was just thinking that since soil moisture is essential for much of the motion that you get, either heaving or thawing and settling or downslope displacement, the local source of water is going to be critical. And so, but we don't normally have a way to characterize that. And I thought that INSAR could actually do a good job.
Probably, yeah. I mean, if you pass one surface over the other, like elevation change in snowpack, yeah, that might be a cool thing.
Yeah, and I think there are a couple other remote sensing data sets on snow depth and snow, estimates of snow volume. I'm less familiar with those, but I know for our study in Colorado, the snow was what we were trying to avoid because we were trying to measure the total volume of the bedrock moving and velocities. So we didn't pay as much attention to the snow with the INSAR data, but
yeah, thank you.
Okay, well, I think we will end it there at 1 minute past the hour. I'd like to thank Matthew and Joan Marie for two really great talks. And SAR and INSAR, I think, are going to be very valuable tools for our community in the future. So thank you for sharing your work and motivating all of us, I hope. Before we go, I want to plug, yes, there's a link to next month's event, which I believe is May 22nd. It will be a presentation by John Major. And if I can share my screen, we have a flyer for that. So this talk will be on volcanic processes and geomorphic effects, exceptional and sometimes long-lasting landscape and societal impacts. So please be on the lookout for an email from us with regard to that and join us then. And with that, I would, just like to thank our speakers again and thank you for joining us. We'll see you next time.
Thank you.